Welcome back, everyone. So we're in 6.3, volumes of cylindrical shells. So this is an alternative method to doing discs or washers when we have a curve whose region is a little bit tricky to work out with discs or washers. So we've got our first example down below here. So we have the curve 2x squared minus x cubed. And so we'll ignore the setup here. You can read that on your own, but we can kind of figure out what we want to do here. We would normally, so we're rotating it about the x-axis, so normally we would make this a function of y, but you'll see here that if we do it as a function of y, we're rotating the same region about both spaces. Right, so how do we work through that? Well, we would have to split this up into multiple integrals possibly, and subtract volumes, etc. But it would be much nicer if I could figure out a way to do nice vertical slices as my cross sections, because this would be really easy to rotate around the y-axis if we had that. So that's where cylindrical shells are going to come in. So note, discs and washers, we're always perpendicular to our axis of revolution. For cylindrical shells, we are always going to be perpendicular to our axis of revolution. Cross sections will be perpendicular, or parallel. So let's look at our cylindrical shell here. So if I have a cylindrical shell, so it's going to be a cylinder with a hollow center to it, and it's going to have some width, so we can see that we've got our region rotated about the y-axis here. So the height of the shell obviously is going to be f of x. So f of x is the height. The width is going to be delta x. So you can see here, this really small little sliver is going to be delta x. And so we've got that, and then we have to figure out, well, what is that hollow region, right? How far is that hollow region out? So that's going to be our radius. So in this case, our radius is just x. In a lot of cases, it's going to be just x. So we want the radius, we want the function as the height, and we want the delta x value. So if we looked at that, and we took this shape down here, and we were to cut it, slice it through with a knife, and then we were to unpack it, what you'd end up with is the circumference of the cylinder, so the circumference of that circle, that little width, and then the height. So we end up with 2 pi r h times delta x, which is going to give us our volume, right? So that's going to be the area, surface area of the cylinder times the width, which gives us the volume. So for integration purposes then, right, we need to figure out a way to cut this so that we have an infinite number of shells. So what we're going to do is we'll vary our x sub i's like we normally do. Delta x we'll do as a fixed width for each cylindrical shell, and then we'll take the limit as n goes to infinity, shrinking that width of each shell to an infinitesimally small value. And so what we end up with is this guy, the integral from a to b of 2 pi x f of x dx. If we are doing it with respect to rotating about the x-axis, then the only thing that'll change is we'll integrate along the y-axis, of course, from c to d, and then we'd have 2 pi y f of y dy. Right? So it's going to be the same if we're dealing with functions of y as well. All right. So back to our example. So we want to actually find the volume of that region. So our curve looks something like this. Zoom in a bit. Again, we're rotating it about the y-axis. So if we take one particular cross-section that we're looking at, we can see that r of x is just x. Since our distance from the x-axis is just x. The height h of x is going to be 2x squared minus 3x cubed. Is that what our function is? Minus x cubed, sorry. All right, and so we're done. So now we just need to figure out how to integrate this along the axis. So we've got 0 there, our other 0. So now if we set our equation equal to 0, we'll see that 2 is where we reach the x-axis again. So we're going to be integrating from 0 to 2, each one of those shells. So our volume is going to equal 2 pi integral 0 to 2 of r of x, which is just x, times h of x, which is 2x squared minus x cubed dx. And then this becomes a pretty simple integral. So we'll have 2x cubed minus x to the 4th. And so what we're going to end up with is 2 pi. We'll have x to the 4th over 2 minus x to the 5th over 5, 0 to 2, which is going to give us 2 pi. 2 to the 4th is 16, so we'll get 16 over 2 is 8, and then 2 to the 5th is 32, so minus 32 over 5, so we can change our 8 to 40 over 5. It looks like we're going to get 8/5 times 2 pi, which is 16 pi over 5. Okay. So again, much easier than if we tried to work through some sort of a washer method of splitting the region where it reaches its maximum point and splitting it into 2 separate volumes. Okay. So we've got some more examples here. So I think I'll stop the video here and then we'll come back and finish these examples. So if you have questions, send me an email. Otherwise, come by the office hours. And until next time.